In this video, we're going to talk about implicit differentiation. Implicit differentiation is the technique that you want to use when you need to take the derivative of implicitly defined functions. And remember, we talked about what implicitly defined functions were in the previous video, right? Those were functions that were guaranteed under certain conditions to exist by the implicit function theorem. And that's when you have, an equation that maybe when you look at the entire equation, it's not it doesn't define y as a function of x, right? But you can look at parts of the equation, and it will define the smaller pieces will define functions in there. So we don't need to be able to solve for y in order to take the derivative. That's important to know. So we don't need to be able to do that. And one of the things that you always need to keep in mind, right, is that the variable y in these equations, it's best to think about it as taking the place of some more complicated function of x. If you don't, if you kind of don't internalize that part there, then it's going to seem a little mysterious. So always keep that in mind. When y is in there, it's some more complicated formula. Remember how we had equations and we solved for y, we got y equals some function of x, right? When we were talking about, say, like x squared plus y squared equals 1, we solved for y and got that y was square root of 1 minus x squared, right? So y is essentially the same as the square root of 1 minus x squared there. It's a more complicated formula when it appears in there. What that means is that anytime you take the derivative involving the variable y in here, it's going to wind up to be a chain rule problem. Okay, and that's extremely important to keep in mind. All right, let's take a look at an example, and let's just start with the one that we've been talking about, x squared plus y squared equals 1. We want to find the derivative of any implicitly defined functions in there. So dy dx. Okay, so we have this equation here, and what we're going to do is take the derivative of the left-hand side and then set it equal to the derivative of the right-hand side. All right, so let's go ahead and get that process rolling. If I look over here on the left-hand side, this is the sum of two things, right? X squared plus y squared. So I'm going to use the sum rule and take the derivative of x squared, and then I'm going to add the derivative of y squared to complete the derivative of the left-hand side. So the derivative of x squared is 2x. Then I'm going to put a plus. Okay. Then I am going to take the derivative of y squared. Okay, so again, it's important to remember that y, right, is not just a variable like x is, right? Y is taking the place of some more complicated function of x. So I always try to think about, hey, there is some function of x underneath there. I can't really see it, right? It's behind the y, so I don't really know any of the details about it, right? We haven't solved for y here, so we wouldn't really know anything about it, other than there's some more complicated formula in here. Okay, so I'm going to take the derivative, right, 2y, that would be the derivative of y squared using the power rule, right? And remember, y is taking the place of some more complicated formula in there, so this really becomes a chain rule problem. And the last step of the chain rule, right, if you remember that, is to multiply by the derivative of the inside part. Here, y is the inside part, right? And so I need to multiply it by its derivative. Well, you may say, well, if I don't even know what y is equal to, how can I say what its derivative is equal to? And you can't exactly, but we can put sort of a placeholder in there to represent that, right? The derivative of y with respect to x, right? In symbols, we would just have dy dx. And so that is the derivative of y squared. And then we're going to put the equal sign. That's the entire derivative of the left side. Now take the derivative of the right-hand side. The derivative of 1, it's just a constant by itself, right? So the derivative is 0. Okay. So again, right, most people's reactions when they see this for the first time is, what is going on with the dy dx? Where did the dy dx come from? And just think about it in this way, right? It came from the chain rule. But imagine if it wasn't y squared, but if it was sine of x inside there being squared, right? If it was sine of x inside there being squared, you would say, well, sine, this is a chain rule problem, right? I have sine x on the inside and x squared is the outside function. So I would take the derivative, right? Using the chain rule, right? And so I would take the derivative of the outside, bring that 2 down, drop this power to 1 using the power rule, then leave the inside part alone, right? And then the very last step would be to multiply by the derivative of the inside part. Well, the inside part we know, right, is sine x, and so its derivative will be cosine x. Okay, so we're able to do that no problem. Well, that's essentially exactly what was going on when we were taking the derivative implicitly, right? We had y squared, right? So in this case, we didn't really know what the function was inside there. We know y is taking the place of some more complicated function. We just don't happen to know what it is right at this moment. Here we knew exactly what it was, right? Because that was explicit. It was sine x, okay? And so we knew what the inside function was there. So when we take the derivative here, we were, again, using the chain rule just like we did before. Brought the 2 down, dropped this power by 1, left the inside part alone, right? Here we didn't know the inside part, but whatever's inside there, we're going to replace it again. Okay? And then the third step of the chain rule is to multiply by the derivative of the inside part. Back when in this part where we knew the inside part was sine x, we could easily say, hey, the derivative of the inside part will be cosine x, because we knew what this was. Here, all we know is that that is taking the place of some more complicated formula, and so therefore we couldn't really say what the derivative of y is, so we just put this symbol right here, dy dx. Hey, if you ever figure out what y is, just put its derivative right here. In the meantime, we're just going to put this little symbol right here to denote that we completed the chain rule, right, by multiplying by the derivative of the inside part. Okay, so that's where the dy dx came from. All right, so that's the equation that we got after we took the derivative. Once in some of these problems, that's all you need to do is to solve for dy dx and get a formula for the derivative here. So let's go ahead and do that. What we would do is subtract 2x from both sides, right? And our goal is to get the dy dx by itself on one side. So first we would add or subtract, right? And here we're good. We subtracted that minus 2x over. And now to get the dy dx by itself on one side, we would just divide both sides by 2y. Okay, and so that's what we would get. And then of course we can simplify that. And we get a formula for dy dx. dy dx is equal to minus x divided by y. One thing that you'll notice here is that these formulas involve both x's and y's right here. And that's sort of the price you pay for not solving for y first, or for it being impossible to solve for y, or very difficult to solve for y. If you have an explicitly defined function, then your derivative will just have x's over on the right side, and that's it. But if you have an implicitly defined function, your formula for the derivative is going to have both x's and y's in it. All right, so that is the derivative, right? We found the derivative of any implicitly defined functions by doing this here. There is one sort of question that's hanging out there, and that is, if we solve for y and then take the derivative, does it agree with the implicit method? All right, so let's check that out. For x squared plus y squared equals 1, in the previous videos we've seen that if we solve for y, one of the functions that we get, one of the implicitly defined functions, is square root of 1 minus x squared, which we can write as 1 minus x squared to the 1/2 power. Let's take its derivative now that we have it written explicitly. The derivative is going to be a chain rule problem, right? So I'd bring the 1/2 down and subtract 1 from this power, right? Using the power rule to take the derivative of the outside. Step 2 of the chain rule, I will leave the inside part alone. In step 3 of the chain rule, I will multiply by the derivative of the inside part. Okay, and just cleaning that up a little bit, if I multiply 1/2 times -2, I'll get a -1, so that's where this negative sign came from. The x I'll just put on top, and since all this expression here had a negative exponent, right, I'm going to move it down to the bottom part of the fraction and get 1 minus x squared to the 1/2 power. All right, so that's the derivative of this function here, the function that gives the top half of the unit circle. So if you remember when we took the derivative implicitly, right, this is the result we got, dy dx equals minus x over y. Okay, and so it looks a little different at first, but then if you remember, hey, this is explicit now, and we know what y is equal to. Y is equal to 1 minus x squared to the 1/2. We have it explicit now. So if we plug that back into this formula for y, we'll get exactly the same derivative that we got taking it the explicit way. So in fact, right, the implicit method does agree with the explicit method when you're able to solve for y, right? But the advantage of having the implicit method is that I don't need to solve for y, and if it's very difficult or maybe even impossible, I can still take the derivative of those implicitly defined functions.